Okay, welcome to lecture here. There we go. And we'll be picking up where we left off yesterday with our last chapter here about kinetics. Sorry about that. Computer decided to update at the wrong time. So we'll just give everybody a second just to get in, and we'll continue on. Okay, so we are continuing on here with kinetics, and we started talking about kinetics. And remember that kinetics basically tells us about how fast or sort of slow a reaction proceeds. Again, a little bit different than thermodynamics that we were talking about in previous chapters, where we focused more on whether or not a reaction would be spontaneous or not, which basically just kind of tells you whether or not the reaction would occur. But here we're looking more at sort of the rate or how fast or slow a reaction will occur. And we talked about a couple of different things to sort of begin with in this chapter. And we talked about the idea of sort of what's referred to as the rate expression. And the rate expression is where we can take a balanced equation. We could use the coefficients. And we basically could figure out how the overall average rate for that particular, and we also can figure out things like how reactants are changing with time, how products are changing with time. And we do these basically as sort of derivative type things. So like changes in concentration over changes in time. And when we talk about sort of our reactants, as we would expect, again, a little bit different than a lot of reactions we talked about this semester. These are really mainly sort of one-way streets. So things are going from reactants to products in sort of a one-way direction. And what that means is when we think about how our reactants are changing over a period of time, they should be decreasing. And we saw some graphs, so obviously the reactants coming down. At the same time, our products should be increasing. And we can basically represent that with sort of our rate expression, where we can, for example, come up with something like we have this reaction, the rate would equal minus 1 over A, the change in the concentration of A over the change in time. And we can also write one for our products. For example, the rate would equal minus 1 over C, change in concentration of C over the change in time, except our products would not be negative. It would be a positive rate change there. And we do have the negative here because it's decreasing with time our reactants, and I miswrote there, so I'll just cross out really good. This is actually positive on this side. And we get 1 over the coefficient. And I'll get to your question in just a second, actually. So we could use this to help us decide in terms of what's happening in the reaction, we pretty much just need to know one particular thing. And if we know how, say, A is changing, we can figure out how B is changing, how C is changing. We can also figure out the overall rate. And another reason why the reactants have that negative in front of it is, as we talked about last time, when our reactants are losing concentration, that means when you do the final minus the initial concentrations, you will get a negative number. And that negative number plus the negative that's in the formula here will turn that two negatives into a positive. And typically speaking, when you calculate for the rate, it should be a positive number. So the rate could be a positive number. How the concentrations of reactants are changing will probably end up being a negative number. How the concentration of the products are changing over time will end up being a positive number, again, just to indicate negative sort of decreasing with time, positive increasing with time. So we could use this, and the 1 over the coefficient is important because it takes care of, as we talked about last time, really the stoichiometry that's involved in that equation. So remember that for these reactions, really to proceed correctly to the product side, they need the proper sort of mole to mole relationship or ratio. And that would give them a certain rate that would occur based on, you need 2 moles of this guy and 1 mole of this guy. So you do have to take that into account when you're kind of doing the rate expression there. And that's what the 1 over the coefficient does for you. We also talked about that if you wanted to, you could kind of do a basic stoichiometry problem first and then kind of go into it and do the mole to mole relationship. But it is sort of the same thing. Now, this is not to be confused with sort of rate laws, which is where we sort of finished up on this slide here. And a rate law has this generic sort of form like it is in the middle there, that the rate is equal to K times the concentration of our first reactant to the X and the concentration of our second reactant to the Y, for example. Those X and Ys are what are referred to as orders, and they are, X would be in this example here the order with respect to A, Y would be the order with respect to B, and those guys are found sort of experimentally, which means in these type of problems you're typically given tables, and you can use those table and that table information to figure out what the orders are experimentally. They are not the coefficients in the balanced equations. So again, at this point, we're used to using those coefficients a lot in calculations, but here's a place where we do not do that. So you do have to find them experimentally. Now, the orders, again, you could kind of think about it as sort of the proportion of, A and B that needs to sort of mix together correctly, in the sense of providing enough reactants to give us a certain rate for a particular reaction to occur. You could get the overall order of a reaction by adding those together, the X and the Y, or if you had another one, X, Y, and Z, or whatever letters you like there. You could add up all the orders, and that will give you the overall order for a particular reaction. Now, when you go to these tables, as we'll see here in a second, most people will do some type of mathematical approach to sort of figure out what is happening. And really what you're looking at when you go to these tables is you're trying to figure out, as the concentration changes, as it increases, maybe decreases, however you want to kind of look at it, how is that affecting sort of the rate of a particular reaction? So for example, if we like double the concentration, does the rate double? If we quadruple the concentration, does the rate double? Does it quadruple? Does it go like 16 times as fast? So this is sort of what you're looking at when you look at these tables. And as I sort of wrote on the right there of the slide, typical information that's sort of given to you in these tables are several different trials that were done experimentally. And in these trials, you're typically given the concentrations of the reactants. You're also usually given the initial rates that were sort of determined in the experiment. By the way, they would determine that by doing some type of graph or something like that, usually, where they do take the molarity over the seconds, or how the molarity over the seconds is sort of changing for that particular experiment. And basically what you're looking for is, you could solve for these things sort of mathematically by using this formula that we talked about here at the very end last time, which is over here. And where it says rate 2 over rate 1 equals Ka to the X, B to the Y, basically what you want to do is go to the table and choose 2 entries in that table. Again, rate 2 and rate 1 doesn't mean that you have to take like the first entry and the second entry. But basically what you're looking for when you go to that table is you're looking for 2 entries where one of the concentrations remains the same and the other one sort of varies. And the purpose of that is, mathematically speaking, right, when we solve for unknowns, we don't want a ton of unknowns, right? So we want to kind of minimize the number of unknowns we're trying to solve for. So you want to pick one if you have 2 reactants where one of the reactants remain the same, the other one varies. So in the made up a table that I did there on the right, if we look at experiments 1 and 2, the concentration of A was 4, the concentration of A was 4, and the second one, that is constant. While if we look at the concentration of B, it was 2, and then in the second one, it was 4, so it varied. So those would be 2 good entries to use. And to answer the question that was asked, when we talk about rate 2 over rate 1, if you sort of usually want to hit maybe nicer whole numbers, usually what you'd want to do is take the sort of larger rate on top and the smaller rate on the bottom. Does it always have to be that way? It doesn't. It just will not give you, you might not get nice, pretty whole numbers. So you might get decimals and stuff like that, which you could solve for using the natural log and stuff like that. So it'll come out the same as long as you keep all the information the same. So whatever you choose for like rate 2 and go all the way across on top there, you need to use obviously all the information from that table to do that. And then whatever you choose for rate 1 and go all the way across, you need to use all the same numbers. So when I say that, typically speaking, you want to maybe put the larger rate number on top and use all that information up there on top. The point of that is usually it'll give you, I won't say always 100% pretty, perfect, nice whole numbers, but you most likely will get more whole numbers than maybe decimals if you flipped it. If you flipped it, like I said, may just require a little bit more math to figure it out, but you could still figure it out. It'll come out the same regardless, as long as you, again, just kind of keep all the information together. So the point here is when we got down here, we actually put some of those numbers in. And when we divided out the rate, for example, here on the bottom, we found that we got 2. As we talked about when we went through this, K and K is the rate constant. Although we don't know what it is at this point, we do know that it's going to be the same number, so they will cancel. Because we held A's concentration the same on the bottom here, those 2 guys will also cancel because the X value for the order will be the same for both of them. And then that allowed us to get 2 to the Y equals 2, which I translated up here on top at the end. And again, you could, something like this, which is sometimes the benefit of like the whole number sort of approach, you could kind of easily look at this and go, oh, I know Y needs to equal 1. Again, if you got like 0.5 and something else on the other side, you may not be able to just kind of quickly look at it and determine what the exponent may be. It may require you to do the calculation part, which, by the way, if you need to, you would take, for example, in this particular one, you take the natural log of 2 on the left and then divide it by the natural log of, in this case, 2 on the right, which would obviously give you 1. Because when you take the natural log, for example, of that 2 to the Y and you take the natural log of it, it just becomes 2 to the Y, basically. The Y comes down, I'm sorry. The Y comes down and you get the number in front and then you can divide it. So that's sort of mathematically, if you get one that's maybe not so clear as to, I'm not really sure exactly what the number might be, that's sort of the approach. One approach to solve for that, again, is just to kind of natural log both sides and divide, and you'll be able to get what the value of that exponent is. Any questions on that stuff there? So let's take a look then at an actual table for this particular reaction that we've been looking at. And again, this is very similar to the information that would be perhaps provided in a problem. This particular table has 3 entries in it. You very well could have a table that's got like, 12 entries, 13 entries, 14 entries, however many entries there are. But most likely you may have like 3, most of the time, maybe 4 entries and so forth. So again, when we do this, we could try to solve this mathematically. We could write our generic rate law for this. And again, it would be the rate is equal to K times the concentration of F2. And I'm going to call it to the X times the concentration of ClO2 to the Y. And again, a reminder that the rate law, different than sort of the rate expression that we were talking about, as you can see, only deals with our reactants. So no products involved here in the rate law. It's just the reactants that are the important ones in determining the rate, because essentially the idea here is we're not starting with any products. So everything that in terms of the rate of how fast it's going to occur is all really solely based on those reactants coming together and basically initiating that reaction. So we could use that formula where we saw rate 2 over rate 1 equals K to the F2 over X, ClO2 to the Y, and K F2 to the X and ClO2 to the Y. So when we're doing here, we want to choose, again, two entries where one of the concentrations remain constant and the other one varies. So if we look at entry number 1 and entry number 2 in this case, the concentration of F2 remains constant, while the concentration of the ClO2 will vary. And if we look at experiments 1 and 2, we could substitute this into here. So for this one, experiment number 2, we have an initial rate of 4.8 times 10 to the minus 3. That is the larger number, so I'm going to put that up on top. So up on top, I'm going to put all the information from experiment number 2 in that table, which would be this, equals K. The concentration, my F2 is 0.1, sorry, to the X, and 0.04 to the Y for my ClO2. So everything that I wrote here all came from entry number 2 in the table. I'm then going to divide everybody here by entry number 1 in the table. So that would give me 1.2 times 10 to the minus 3, K, 0.1 to the X, and 0.01 to the Y. So at this point, we can now do some math here. When we divide these two numbers, we end up with a 4, I believe. Just like we talked about last time, we don't know what the rate constant is, but we do know it's going to be the same value. So that's going to cancel. Again, here at this point, we don't know what the X is, but we do know it's going to be the same number. So since we held this constant, this will also cancel. We don't know what the Y is, but it will be the same number. But we have 0.04 divided by 0.01, which gives me 4 to the Y. Again, here, this one you can kind of easily figure out, hopefully, that Y equals 1. So the order with respect to the ClO2 in this equation is a first order with respect to that. Now, once we did that, what we want to do is go back to our table. And since we held the F2 constant the first time, what we want to do now is hold the ClO2 constant. And to do that, it looks like entry number 1 from the table and number 3 from the table will do that. So we're going to look here at experiments 1 and 3. We're going to do the exact same thing. So in this case, looking at the rates, I see that the third entry in the table has the larger rate. So I'm going to put all the information for number 3 up on top. So that's going to give me 2.4 times 10 to the minus 3. Okay, my concentration of F2 is 0.2 in this case to the X and 0.01 to the Y. And then I'm going to put all my information from number 1 on the bottom, which should be the same as what I got going there on the other side. 1.2 times 10 to the minus 3, K, 0.1 to the X, 0.01 to the Y. Again, we're going to do a little math here. So that's going to give me a 2. Same deal. Don't know what K is, but it's going to be the same. I do know over here, these guys are going to completely cancel out because I held them constant. So now when I divide this, I end up with 2 to the x. Same deal, you could probably figure it out just looking at it, that x in this case does equal 1. By the way, it won't always be 1. It can be other numbers. It just happens in this case that it is 1. So by doing this, we have now mathematically figured out the orders of this reaction based on the information given to us. And we now can write the completed rate law. And the completed rate law would look like the rate equals K times F2. And just like anything else, you don't have to put the 1 there. It's implied. And you can put ClO2 also to the first, so you don't technically have to put it there. And this would be the completed rate law with the proper orders. So the question is, I'm assuming you're asking at this point, will you always get a whole number? And so the question is, will you get a whole number there? And the answer is, in a real experiment, maybe not, but you might get close to a whole number. I would say in probably most book type problems, you'll probably get fairly close to a whole number, or pretty close to round, to sort of round if you needed to. In a true experiment, if you actually did an experiment, you might not get right at a whole number and stuff like that. But I would say probably for book type numbers, probably going to be similar to that. Okay, I see. There's another question. Perfect. Yeah, so that's also a very good question. So this is what we were talking about earlier. This is why you cannot just take the coefficients as those exponents. As you can see here, it doesn't match. It matches for F2, but it doesn't match for the ClO2. So the coefficients are needed, and the mole-to-mole relationship is needed, obviously, to keep up a certain rate. But it won't always end up being the order, for example, for the reaction in terms of sort of proportion-wise to maintain that rate. Just read the questions real quick here. Okay, so let me just review a couple of things, which I think will cover some of the questions here. So first off, to choose the 2 experiments from the table to use in this sort of mathematical approach, what you want to do is you want to pick 2 entries where basically one of the concentrations remain the same and the other varies. And really the purpose of that is so you really only have one unknown to solve for. So like in the first one, we had Y was the only unknown to solve for. For the second one, the X was the only unknown to solve for. If you pick 2 entries where everybody's varying, you'll have 2 unknowns, and you really won't be able to solve for it, either the X or the Y, for example. So that's how you go about sort of choosing. You want to choose 2 entries where one of them stays the same, the other varies. If you happen to have 3 reactants, then you would want to choose, one where 2 of them stay the same and one of them varies. So I would say most of the time 2 reactants is probably what you'll see, but you could have a reaction that has like 3 reactants. So if you do have that, then you would have 3 reactants in the table. You would want to choose where 2 stay the same and 1 vary. So really that's the key. You just want 1 unknown. And so that's really the purpose of how to choose which ones to put in there. And again, the rate law is determined by sort of the proportion that really needs to come together to maintain that rate in terms of how fast or slow that reaction will take place. So in terms of the stoichiometry of the reaction, you need a 1 to 2 relationship for the F2 to Cl2 for that reaction to sort of proceed to the products. To maintain a particular sort of rate that's going to occur when this reaction occurs, as you can see from the rate law, you kind of need almost I want to say a 1-to-1 relationship. That's maybe not the right way to word that, but sort of an even number of proportion of those guys to maintain a particular rate. So that's sort of the slight difference in terms of, why the coefficient is not necessarily the exponent here. 1 you're focusing in on in terms of the rate law, the sort of the proportion you need to maintain a particular rate for that reaction to take place. The second one is in terms of just a regular stoichiometry is just in general for that reaction to take place, you need a certain proportion to produce products. So that's the sort of slight difference in terms of, again, why the coefficient is not necessarily the exponent. I think that hopefully got all the questions, I think. Okay. So a couple other things that we could do once we have now basically gotten our completed rate law is we could figure out the overall order of this reaction. And the overall order is simply taking both of these orders and adding them together. So 1 + 1 gives you a second order reaction overall. So overall, as a whole, this reaction was referred to as a second order reaction. And we're going to see second order reaction a little bit later on in this chapter in terms of sort of what's going on in that case. The other thing that you could figure out once you figured out the orders of each of the individual reactants is you can now find the actual value of the rate constant once you've done this. And because we already know that the orders of everybody in this particular example here, and again, I'm just going to put the 1 in here. You don't need to write the ones normally. But now that we have these orders basically figured out, we could use this completed rate law to actually figure out the value of K. So in this particular case, if we rearrange this rate law, K would equal the rate divided by the concentration of F2 divided by the concentration of ClO2. Now you may ask, where do I get these numbers from? And where you would get these numbers from is this table right here. So once you've completed the rate law with the orders, you then could go back to this table and actually solve for the value of the rate constant. Your question may be, does it matter which one I choose here? And the answer is this is a rate constant, which means technically speaking, no matter which experiment that you choose from that table, it should end up with a constant value for that. So you could choose any entry in that table to solve for K. You could choose entry 1, you could choose entry 2, choose entry 3. The only thing obviously you can't do is you cannot just mix and match. So if you choose entry 1, you need to use all the information for 1, entry 2, all the info for entry 2. So just to get a value here, I'm going to take all the information from entry number 1 and put it in. So for number 1, our rate is 1.2 times 10 to the minus 3 molar seconds. We're going to divide it by the concentration of our F2, which is 0.1 molar. And we're going to times that by the concentration of our ClO2, which is 0.01 molar. Again, here I chose entry number 1 to solve for the value of the rate constant. And I just put in all the values. And when I do that, I end up with a number that maybe looks like 1.2. Now, when we get this number, we also have some units that go with it. And units of rate constants are really important. So if you look at the units, this molarity here, for example, we'll cancel that molarity there. And we will end up with units of 1/molar seconds. Or if you want, you could write, obviously, m-1, s-1, right, which is the same thing. And the units of the rate constant, as I might have mentioned yesterday, but I'll mention it now as well, the units of the rate constant will actually tell you the order of the reaction. So when we see units of 1/molar seconds, for example, those are the common units that are associated with, not surprisingly, a second order reaction overall. So again, the units of the rate constant oftentimes will tell you a very valuable sort of piece of information, and it will, again, allow you to know the order of the overall reaction. And that's really important because there's a lot of problems in kinetics where, as we will see and as we continue on, they will not necessarily in flashing lights go, hey, this is first order reaction, this is second order. They will just, again, give you the value of the rate constant with the units and expect you to know what order of the reaction or what type of order the reaction is. And that's really important for you to later on sort of choose the correct formulas to use. So I think the question is, how do we know it's second order over here? I think that's your question. Yeah. Yeah. So we know it's second order. So once you've completed the rate law like we did previously, and we found out that y equaled 1 and x equaled 1, right, for each of those are the orders with respect to the individual reactant. So the order with respect to F2 was 1. The order with respect to ClO2 was also 1. When you want to find out the overall order of a reaction, you basically add all the orders together. So 1 plus 1 equals 2. And that's how we know it's second order overall in this reaction. And again, if you had, say, 3 reactants, you would add up the orders for all 3 of them, and that would give you the overall reaction as well. Other questions on that? Okay, so let's see what we got going here. So a couple of things that we sort of touched upon, I think, here with this one, but let's just reiterate here a couple of them. Again, rate laws are always determined experimentally, which means, as we see with this particular table here, you will be given usually some type of information in a table in these type of problems. Reaction is always in terms of reactants, so no products involved in our rate laws. And as we saw with this particular example here, the order of ClO2 does not match the coefficients. So again, we cannot just take the coefficients and use those for our rate laws. Again, the slight sort of difference between those two things, as I mentioned before, is when we're talking about the rate law, we're talking again sort of the proportion that's needed of those reactants to maintain a particular rate, as opposed to the proportion that's needed for the reaction to sort of take place and actually just occur, which is sort of the mole to mole relationship or the stoichiometry part of it. All right, so I think this is the one you have next, I hope. Yeah. Let's see. Why don't you give this one a go? The rate equation for the reaction of NO and ozone is the rate is equal to K NOO3. If the rate constant is 6.6 times, if the rate is 6.6 times 10 to the minus 5 molar seconds, what is the rate constant? Why don't you calculate that real quick? Okay, so let's take a look at this one here. So they did give us the rate law. So our rate is equal to K NO and O3. And we want to solve for K in this case. The overall order here, by the way, is also second order, as we have a 1 and a 1 for the individual orders here. So again, if we solve it just like we did on the previous one there, the rate would equal our NO and our O3, and they gave us all these values here. So this is going to be 6.6 times 10 to the minus 5 molar seconds divided by our 1 times 10 to the minus 6 molar. and our 3 times 10 to the minus 6 molar. Again, in terms of units, molarity and molarity is going to cancel. That is going to give us 1 over molar seconds. And the number we will have, making sure we use our exponent button, just to make sure here, 6.6 minus 5 divided by 1 to the minus 6 and divided by 3 to the minus 6 gives us a rate constant of 2.2 times 10 to the 7. Units are 1 over molar seconds in this particular case here. Any questions on that? Again, our units here match our second order reaction in this particular case. Any questions on that particular one? Okay. And that's a pretty big rate constant, which means probably the reaction is occurring pretty quick. All right, so why don't you give this one a go? We got a table here. Why don't you determine the rate law with the orders and the value of the rate constant here? So figure out the rate law, the rate constant, and all that good stuff, the overall order and all that good stuff here. So rate law, figure out the overall order and the value of the rate constant. Yeah. All right, so take a couple minutes here and see what you come up with, and then we'll talk about it. Okay, let's take a look and see. So again, you can start with sort of the generic rate law here. So in this case, the rate would equal K times the concentration of our first guy there to the X, and our second guy there to the Y. So again, the goal here is if you want to solve it sort of mathematically, you can, again, look for two entries where something remains constant and something varies. So if we look at entry number 1 here and entry number 2, so 1 and 2, the concentration of S2O3 S2O8 remains constant, while I minus varies. So again, here I'm going to go with number 1 on top just to get some whole numbers. Again, you don't have to. You can solve it the other way if you want. But so I'm going to go 2.2 times 10 to the minus 4 up on top. K times the concentration of 0.08 to the X. 0.034 to the Y. Again, everything here up on top is from entry number 1. We'll go to entry number 2 in the table, do the same thing. 1.1 times 10 to the minus 4, RK, and 0.08 and 0.017Y. So sort of the same approach. This is going to give us a 2. Again, our rate constant, not sure what it is, but it will cancel. This, not sure what X is, but it should cancel. And again, when we divide our back end here, looks like that is a 2 to the Y. So in this case, Y is going to equal 1. Again, that would be the order with respect to I minus. So what we want to do next is, now that we held the first guy constant, we want to go back and hold the I minus constant. And to do that, it looks like entry number 2 and 3 will do that. So if we take number 2 and 3 and put it in this case, I'm going to go with number 3 on top. Again, the larger rate sometimes will give you that better whole number. And again, we got 0.16 in this case. And 0.017. And again, everything on top is from entry number 3. Everything on the bottom here from entry number 2. So when we do this, that's going to give us a 4. Again, the K is going to cancel. This guy we held constant, so he's going to cancel. And when we divide here, we get 2 to the X. In this case, you should hopefully also be able to figure that out. X is going to equal 2 in this case. So the order with respect to the S2O8 is second order. That would give us a completed rate law of the rate is equal to K times our S2O8 2 minus squared times our I minus, which was 2 the first. This overall order, I'll just borrow the writing here, is 2 plus 1, which technically would be a third order reaction in this made up reaction. Any questions so far how to sort of solve it mathematically? So I've been talking about solving it mathematically. Sort of the non-mathematical approach, if you will, is to, if you understand how things change, for example, in the experiments 1 and 2, what we see is that as we double the concentration, the rate also doubles as well. So it's sort of like a 1-to-1 relationship there. And thus we ended up with an order of 1. While as we sort of quadruple, as we, on the second one, we doubled the concentration, the rate went up by a factor of 4. So it's like a 4-to-2 relationship, which reduced down to like a 2. So that's sort of the relationship there if you kind of don't do it mathematically. So for this class, if you choose not to do it mathematically, you do need to explain it in words why you chose those, not just randomly. I chose a 2 and a 1. So That's sort of the other approach, is a sort of non-mathematical approach. If you sort of understand relationship-wise how things are changing in relationship to concentration and rate, you could do it that way. But again, for a test or something like that, you would have to do some type of explanation in words as to why you chose that if you're not going to solve it mathematically. So for most people, the mathematical approach is a little bit easier than putting things in words. So that might just be an easier move for you as well. So now that we do have the completed rate law here, we can solve for K. So in this case, K would equal, or H would equal, try that again. K would equal the rate divided by the S2O8 2 minus, and we do need to square it, so that's important, and the concentration of I minus. So just like before, we could choose any entry you like. So I'm just going to choose the first one. So 2.2 times 10 to the minus 4 molar seconds. We're going to take 0.08 molar and square it. And we're going to take 0.034 molar as well. Now we end up with 2.2 minus 4.08, a little square action, and 0.034. Looks like 1.01. Now, unit-wise, molarity cancels here and here. That does leave us 1 over molar squared seconds. Molar squared coming from here, yes. So as you can see, those are different units than what we had for a second order reaction, which was 1 over molar seconds. So again, you really can sort of determine almost what the order of the reaction is based on the units. 1 over molar seconds, if you just count the units, that's 2 units on the bottom, second order. 1 over molar squared seconds, that's molar squared plus a second, that's like 3, that's third order. A normal first order is 1 over seconds or some unit of time, that's like 1 unit on the bottom, which means like first order. So you can kind of figure that out as well. So the question is, do you have to use experiment 1 to figure out the rate constant? The answer is no. Again, you could choose any of these entries in this table and put them in there, and you will get the same answer, I believe. You should end up getting 1.01. And again, you can put it either way in terms of on top or anything like that. Like I said, just on top, the reason, again, I choose I choose the one with the larger rate is not 100% of the time, but probably most of the time, if you do that, you'll get kind of nicer numbers, more whole numbers to kind of deal with when you get to the end, like down in this section. And again, if you don't do it that way, you won't get maybe like whole numbers at that point. You'll get maybe some decimals, which is not bad. You could use the natural log and solve it that way. But it just sometimes makes it easier to do it the other way. Yeah, so if you didn't write, I think your question is if you didn't write 1 over molar squared seconds, you would do, that m to the basically minus 2, right? And then s to the minus 1. I think that's what you're asking. Instead of doing 1 over sort of the numbers there. Other questions on that? Okay. So I think maybe we have another one. So why don't you try this next one? Kind of the same deal. Figure out the rate law and the value of K and all that good stuff. So why don't you take a couple minutes and go for it. Here we do have 4 different entries in this table. Again, you want to approach it the same way. Pick the 2 and then pick another 2. I know. And here you missed the whole joke where I said I knew my microphone was off and I didn't even turn it back on. You know, that was good. All right, so you want to hear me? Probably not, but I appreciate the thought that you do. That's nice. All right, so let's try this again. Third time, microphone's on. I think you can hear me now. That's good. All right, the rate is equal to K times the concentration of our NH4 plus to the X and our NO2 minus to the Y. And again, we're going to do our same sort of approach here. We do have, as you can see here, more than we had in the other tables. And like I said, you could have a lot of different sort of experiments given to you, but really want to follow the same approach. So in this case, I'm just going to start with 1 and 2 because that's going to keep our NO2 minus concentration constant. So if we look at 1 and 2, again, I'm going to go with the higher rate up on top. So 32.3 up on top, 10.8 on the bottom. And again, up on top is going to go everything for experiment 2. So that's going to be K times 0.06 to the X and 0.2 to the Y. And everything from experiment 1 there on the bottom, 0.02 to the X, 0.2 to the Y. So similar sort of approach here. We're going to take 32.3 and divide it by 10.8. We do get something like 2.99. And when you do this side here, these guys cancel. This guy's going to give us a 3 to the X. These guys will cancel as well. This is, you probably could tell if you want, that's probably close enough to 3, and X would equal 1. Now, if you wanted to, again, you could take the natural log of both sides. And if you did that approach, you essentially would take the natural log of 2.99 and divide it by the natural log of 3, and that would equal X, essentially. And if you did that, you essentially get exactly what we got going on there. You get 0.997, which you would most likely round to 1 in this case anyway. So again, just showing you this, that, you know, it may not come out perfectly to a whole number, even if, you know, if you did sort of the natural logs and all that good stuff. In a textbook problem, again, this would definitely be close enough to obviously round to 1 and stuff like that. So in a true experiment, you would also, you know, be close enough to round. So just to kind of show you that technically it doesn't always come out to pretty whole numbers here, but in this case, I personally would have probably rounded beforehand and just went 3 equals 3 to the X and call it a day. But again, if you kind of did this approach, you can see you get essentially the same answer here at the end. Now we've kept the NO2 minus constant. So we now want to keep the NH4 plus constant. And it looks like it's going to be experiments 3 and 4 that's going to allow us to do that. So if we look at 3 and 4, here I'm going to put number 4 up on top as it has the higher number. So 21.6 divided by 10.8 equals my K 0.2 to the X and 0.0404 to the Y, divided by everything for number 3 there, 0.2 to the X and 0.0202 to the Y. Doing this deal here, I believe we got a 2 going on there. Again, going to cancel, and we kept this guy now constant, so he's going to cancel, going to give us a 2 to the Y. So Y, again, in this case, is equal to 1. Again, if you're not sure, take the natural log of 2 divided by the natural log of 2 gets you 1 as well. Is mathematically how you do that. So now that we have the orders for each of these, that means that the overall rate law is the rate is equal to K times NH4 plus times NO2 minus. We also see that the overall order of this reaction would be 1 plus 1, which would be a second order reaction. Again, coming from here and here. And now finally that we have the completed rate law, we could solve for K in this case. And K would equal the rate divided by NH4 plus and O2 minus. And again, here you could choose, in this case, any of the 4 entries. They really should give you the same answer. So if we put it in there, I'm just going to take number 1, for example. I'll do number 2 just to mix it up. So I'm going to take number 2 here just to kind of be different, I suppose. And if we do number 2, we take 32.3 times 10 to the minus 7 molar seconds divided by 0.06 molar times 0.2 molar. You may be wondering, where did I get that from? Because you might have ignored it the entire time, like I kind of did, but it is right here in the table. Doesn't make a tremendous difference in terms of figuring out the orders for, first order, second order, but it does make a difference for the rate constant, because otherwise you're missing that times 10 to the minus 7. So you definitely need to put it in this calculation. Otherwise you will be off. So if you put it in the other calculations we did, like over here, it would just cancel out. So it comes out the same, but you do need to make sure you put it in, obviously, on the other ones there for K for sure. So that would get us 32.3 to the minus 7 divided by 0.06 divided by 0.2. And that gives us 2.7 to the minus 4 as our value. 2.7 times 10. Come here. Try this again. 2.7 times 10 to the minus 4. And unit-wise, molarities cancel. We're left with 1 over molar seconds, although that looks like a G. Not liking when I get to the edge here, apparently. Go that way. So 2.7 times 10 to the minus 4, 1 over molar seconds are capital M minus 1, S minus 1 as a way to do that. So a couple important things. Make sure you do look at the tables, because it's very common people will miss this part of it. And like I said, the reason I sort of ignored it on the first part of the problem is it really doesn't make a difference because that will cancel out. It'll come out the same. You could put it in if you wanted to in each of those steps. But where it really does make a tremendous amount of difference, obviously, is in the value of the rate constant. Otherwise, you will be off by that factor. Any questions on how to figure out the rate law from a table information given to you? Obviously, you need to be able to do that. You need to be able to take a table, figure out the completed rate law, figure out the orders with respect to each of the reactants, figure out what the overall reaction is, order, and obviously figure out the value of the rate constant as well. Any questions on any of that part? Okay, so the next thing we're going to talk about then is actually some formulas that go with specific types of reactions. We're going to talk about 3 types of reactions, which are really the sort of the common reactions in terms of rates or orders that occur, and that is first order reactions, second order reactions, and also zero order reactions. So speaking of zero order, right, if you, in terms of doing these things, just to remind people, right, if I have, 4 to the 0 in terms of, say, an exponent, we all know that that means, hopefully, that equals 1, right? So if you have an exponent to the 0 order equals 1, right? So make sure that does pop up, obviously, when we talk about zero order reactions as well. And you can get some of that in these table ones as well. So, you could get something like, 2 to the x equals 1. X would equal 0 in that case. Again, you could do your natural logs as well and get there. All right, so the first one we're going to talk about is first order, and we actually have seen first order before. And we saw first order kinetics when we talked about radioactive decay. And if you remember, all that radioactive decay pretty much followed first order kinetics. And that's essentially what we're going to talk about here first, just to refresh it. But again, we're going to kind of see it in terms of the actual kinetic sort of symbols instead of maybe nuclear decay. So in a first order reaction, usually we'll have one sort of reactant going to our products. That one reactant will be first order. You could technically have two reactants where the second one has an order of 0, right? Because 1 plus 0 is still first order. So, but most of the time will be probably one reactant. Again, possible it could be two. If we write our rate expression for this, the rate is dependent on the change in the concentration of our reactant. If we write our rate law, which is 1 here, rate is equal to K times the concentration of A. Rearranging K and solving for, rearranging the rate law and solving for K, we just put our units in, we see the typical units associated with a first order reaction, which is 1/seconds or reciprocal seconds. As we might have talked about when we were talking about nuclear decay, it doesn't necessarily always have to be seconds. It's really some 1/unit of time. So it could be seconds, could be minutes, could be days, weeks, years, whatever it may be. In terms of sort of just regular chemical kinetics, as we maybe talked about, usually we don't sit in the laboratory days and days and days and watch an experiment go. So a lot of times what we deal with in terms of time or how long a reaction sort of takes place is usually a lot of times in seconds, maybe minutes. Unless you have a pretty long reaction, you're sitting there waiting for it to take place. So that's why we usually say 1/seconds is a common unit that we associate with first order, again, because seconds is probably usually how long we sort of wait for things to occur sort of in chemical reactions. But again, in reality, it can be 1/some unit of a time. And we really did see some of that in nuclear chemistry where, right, we had 1/weeks, 1/days, we had some of that happening when we did some of those kinetic problems. So there is what is sometimes referred to as sort of the integrated rate law, which is basically the relationship between how concentration is changing versus time. This is sort of our concentration time dependent sort of relationship that we see here. And for a first order reaction, we typically do see two types of graphs. Out of these graphs, the one on the right is most often the one that we see. The one on the left is technically a first order reaction, and the difference between these two graphs is what is being graphed. On the Y over here is just the concentration versus time. And what we see is what we would expect is over time, we start to see our reactant decrease in concentration. And if we sort of go through this equation here and use our natural log function, we get this one, which is technically the first order equation, which is the natural log of A equals our natural log of A naught minus KT, which is really hopefully recognizable to you as the exact same one that we used in nuclear kinetics here, our nuclear chemistry. It's the exact same equation. That means that these guys are the same deal. This is first A is sort of our final concentration. The A with the little naught is our initial concentration. K here is our rate constant. And T is time here. And as we also saw in that sort of nuclear chemistry, that there's a half-life equation, which is the time it takes, obviously, for half of it to disappear. And that's the natural log of 2/K, which is also the same one that we saw in nuclear chemistry. And a reminder, as we talked about there as well, very often you need to use both of these guys together to solve for a problem. So sometimes you're missing some pieces of information, and you can oftentimes need to use the half-life equation to figure out the rate constant and then go into there. Sometimes you do, sometimes you don't, but it's very common. You sometimes will have to use these guys together. Now, the graph that we usually associate with the first order is the one on the right, and that's because if we rearrange that integrated rate law like we sort of talked about maybe a little bit, and write it like this, this is the first order kinetics equation in the form of a straight line. This is y is equal to mx plus b. So what we see is on the y, we have graphed the natural log of a. On the x is our time. And this will yield us a straight line like we see here. And the slope of that line, as you can see from the equation, the slope equals minus k. So the slope is equal to negative k, which means the rate constant will end up being a positive number, because the slope of this line, when you get it, if you graphed it, would be a negative number. The negative and the negative here will turn your rate constant into a positive number. So you'll typically get a positive number there for the rate constant. And again, graphically speaking, it's because you'll get that negative slope. So in terms of first order, much like what we talked about, I think in nuclear chemistry, the important things from this slide that obviously you do need to know, you do need to know the units associated with the rate constant for a first order reaction. Again, as I mentioned before, they oftentimes will not tell you the order, just give you the value of K with the units, and you need to know it. You do need to know, obviously, the integrated rate law here. You need to know the half-life equation, which again, these should be the same ones that you learned for nuclear chemistry. You do need to know the two graphs associated with it. And again, this is the more linear version of that graph, which gives you that straight line. So those are really the sort of the important things that you need to learn or know from this slide. The good news is from that nuclear chapter, most of this should be reviewed this type of order. Any questions on that there? So I think we will stop here today for lecture. And for lab today, it is the first day of our general unknown. And that means followed by the second day of our general unknown. So we will talk about our general unknown in lab, and obviously you'll start working on it today, and we'll continue tomorrow as well. Any questions on anything so far? All right, if not, make sure you put here if you're here, and I'll see everybody in about 10 minutes or so.